Okay, so for finding limits algebraically part one, so kind of the most simple ones to find algebraically, because it's the first one we're looking at, we're going to do it multiple different ways to kind of verify what we're looking at here. And so let's say we have a function, and later on we'll notice this is a pretty nice function. It works out nicely. There's not a lot of complications to it. So f of x equals a polynomial here, 5x squared plus 10x plus 1. And what we're looking for is the limit as x approaches -3 for that function. So what happens when you get really, really close to -3? So we'll go about this a couple different ways. We'll do the easiest one last, just so we can check it out. So first thing I'm going to do is, sometimes it's nice to just see what you're looking at. So picture's worth 1,000 words. I'll just go to y equals, type in my equation, and hit graph. So I can kind of see, well, maybe even if we want a little more insight, you can go to calculate and plug in a number, just so you can see where -3 is. -74. So notice it's like off the screen. Maybe we should zoom out a little bit. Or if I don't feel like zooming out, but I got an idea of what I'm looking at, when we draw one by hand, we can make it a little less to scale. So kind of looks something like this. And we'll say when this hits -3, it looks like the y value or the function value is -74. So that point does exist there. It doesn't need to exist to have a limit. But if it does, it kind of makes your life easier unless something weird's happening around it. That probably should be the limit there. If we want to try our numerical analysis like we did on the other one, so we'll go to the table, then I'm going to go to table settings because I don't want it automatically filling in numbers. So I'll change it to ask. We'll go back to the table, it'll be blank. We can plug in stuff that's close to -3. So we'll start with numbers that are slightly smaller than -3. So like -3.01, -3.001, -3, right? Sometimes that causes a domain issue, and this one's a polynomial, so it doesn't, so that point does exist. And then we could go on the other side, like -2.999, -2.9. Not going to do too many here because we're probably getting the idea that it looks like moves a lot here, but the closer we get to plugging in -3, y gets closer to -74. So let's say if this was a really complicated function that was hard to plug in or hard to graph, we could still get an idea that it looks like our limit is going to be -74. But then other good news, on the ones where you can just plug them in, algebraically, you can go ahead and do that. So now we have a bunch of verification that we think our answer is right, but there wasn't anything necessarily in the beginning that stopped us from just saying, okay, here's my function, and when I plug in -3 for x, what happens? And so I end up with -5 times 9, right? -3 cancels. So -45 minus 30 plus 1. So -75 plus 1, -74. So now we technically did it algebraically, but we have like 3 different sets of verification. We can look at the graph, we can look at the table of numbers, and this one was actually kind of easier algebraically from the beginning. It was one that didn't have a domain issue at that point, so there wasn't anything that just stopped us from plugging in the number and saying, hey, what actually happens when you plug in -3 into this function? And so sometimes it's just as simple as that. Like if you can plug it in, do it. The more interesting limits are going to be the ones that you can't just plug in, and we'll get other methods for those. But first, don't forget to check. Sometimes there's not an issue at that point. You can literally just plug in -3 for x and see what happens.